Imagine rewinding time to the very beginning of the universe, back to the moment of the Big Bang. The conditions in those early moments were unimaginably extreme, so extreme that space, time, and energy as we know them broke down. To understand this mysterious realm, scientists turn to the Planck scale. Named after Max Planck, one of the pioneers of quantum physics, the Planck scale defines the smallest measurable units in the universe. These units help us explore questions like, what's the shortest moment of time? What's the smallest distance? And what happens when we push physics to its limits? Let's start with Planck time, which is approximately 10⁻⁴310 carat, 43, 10⁻43 seconds. How short is that? Well, if the entire age of the universe were compressed into a single year, Planck time would be shorter than a single blink of an eye. It's the smallest slice of time we can imagine, so short that physics as we know it can't describe what happens within it. Next, we have Planck length. At about 1.6 times 10⁻351.6 times 10 carat, 35, 1.6 times 10⁻35 meters, this length is incomprehensibly small. For perspective, if an atom were the size of the observable universe, the Planck length would be smaller than a tree. Scientists theorize that at this scale, space itself becomes quantized. This means space isn't smooth and continuous, but made up of tiny, discrete chunks, almost like pixels in a digital image. Then there's Planck energy, which represents an immense amount of energy tied to these tiny scales. It's so powerful that attempting to measure it would likely create a miniature black hole. This is the energy scale where both quantum mechanics and general relativity collapse, making it crucial for understanding the origins of the universe and black holes. So, what's the significance of all these units? At the Planck scale, our current understanding of physics breaks down. The two major theories, quantum mechanics, which governs the very small, and general relativity, which explains the very large, are no longer compatible. Physicists are searching for a theory of quantum gravity to bridge this gap, and many believe the answer lies at the Planck scale. One of the most intriguing connections is with black holes. The singularity at the center of a black hole is thought to exist at the Planck scale. In this extreme environment, both gravity and quantum effects are so intense that space-time itself may become warped and chaotic. By understanding Planck units, we might one day unlock the mysteries of black holes and their role in the cosmos. Similarly, the conditions just after the Big Bang were likely at the Planck scale. In those moments, the universe was a hot, dense, quantum soup where the usual rules of space and time didn't apply. Exploring this era could provide clues about how the universe evolved and why it has the structure we observe today. These mind-bending ideas remind us that the universe is far stranger than we often realize. We live in a world governed by both the vastness of space and the tiniest building blocks of reality. And while the Planck scale might seem abstract, it's at the heart of some of the biggest questions in physics. Scientists continue to push the boundaries of what we know, searching for a unified theory that can explain both the quantum and cosmic realms. What incredible discoveries might await us as we venture deeper into the mysteries of the Planck scale? The Planck scale offers a glimpse into the smallest, most fundamental aspects of reality. From Planck time and length to the staggering energy tied to these scales, this concept reveals the limits of our current understanding of the universe. What do you find most fascinating about the Planck scale? Share your thoughts in the comments below. If you enjoyed this deep dive into physics, be sure to like, subscribe, and stay tuned for more explorations of the universe's greatest mysteries. Thank you for watching. See you next time.